welcome back to lectures on engineering mathematics 2. This is lecture number 58 on Laplace transform of special functions. So, in this lecture we will cover Dirac delta function, or in particular the Laplace transform of Dirac delta function, also the Bessel's functions and these Laguerre polynomials. So, coming to the Dirac delta function, we usually define through this rectangular pulse, or there are several ways we can define such a specialized or generalized function, where with the help of this rectangular pulse. So, we define this rectangular pulse phi epsilon a as 0 if t is less than a, and between this a to a plus epsilon we define as 1 over epsilon. So, the height is 1 over epsilon from this a to a plus epsilon. Otherwise, so in this region and the region before it is 0. So, this is the so called rectangular pulse function. Now, the first we will get the Laplace transform of this rectangular pulse function, because this Dirac delta function is defined as, or can be defined as, the limiting situation of this rectangular pulse function when this epsilon is very small. So, if this epsilon goes to 0, and this 1 over epsilon in that case will tend to infinity naturally, and that is exactly the function which we will define here as Dirac delta function. So, first we will take the Laplace transform for this given epsilon. So, without considering the limiting situation first. So, getting this Laplace transform with the definition. So, we have e power minus s t, and then this phi epsilon t will be integrated over this function, this variable t. So, here how to get this integral? It is simple, because 0 to infinity, and it is defined from a to a plus epsilon, this function phi epsilon t, or at a also. So, here we have 1 over epsilon, and then e power minus s t is there, and then we have d t. So, because in the rest of the domain this 1 over this phi epsilon a is 0. So, the integral will remain from a to a plus epsilon and e power minus s t because of this Laplace transform. So, here 1 over epsilon, and then here we have e power minus s t over s with minus sign, its integration, and that will be set for the limit a to a plus epsilon. So, here we have 1 over s epsilon, the minus sign we will adjust now. So, first we will put the limit a. So, e power minus s a, and then we have minus e power minus s, and then a plus epsilon. So, e power minus s a is common over this s epsilon, then here we have 1 minus e power minus s, and then this epsilon. So, this is the Laplace transform of this rectangular pulse function, which is written here e power minus s a over s epsilon, and then 1 minus e power minus s epsilon. So, now getting back to this Laplace transform Dirac delta function, which is a limiting situation of this rectangular pulse. That means, this delta t minus a can be defined as the limit epsilon goes to 0 of this phi epsilon a t. So, we already know the Laplace transform of this rectangular pulse function. The only thing we have to deal now, that what will happen now when we take this epsilon tends to 0, because that is precisely the Dirac delta function. So, here in this Laplace transform we will let this epsilon to 0, and we will get the Laplace transform of this Dirac delta function. So, the Laplace transform of Dirac delta function will come as e power minus a s. How to get this? So, we will just set here the limit. So, we will consider that what will happen to this when epsilon goes to 0. So, to deal this here, when epsilon goes to 0, e power minus s epsilon, that is going to 1 minus 1. So, 0 by 0 form we are getting when we consider this epsilon goes to 0. So, 0 by 0, then we can apply the L'Hopital rule, that means we have e power minus s a. There we will differentiate here. So, with minus and minus will be plus s, we have e power minus s epsilon, and then divided by this s, and this epsilon derivative will be 1. So, this s and s will get cancelled. So, we have e power minus s a, and when we take this epsilon to 0. So, this is 1. So, the limit will be just e power minus s a. So, here the Laplace transform of this delta t minus a is e power minus a s. There are some interesting properties of this Dirac delta function, and we will go through them, and then we will look an alternative way of getting this Laplace transform of Dirac delta function through these properties. The first property says, or sometimes it is defined, this is also treated as the definition of this Dirac delta function. So, we have delta t minus a equal to 0 whenever t is not equal to a. So, whenever we are at the point t which is not equal to a, this is defined as 0, and when we integrate this delta t minus a over some interval c to d, and if this c to d contains that point a, then the value of this integral is going to be 1, otherwise the value of this integral will be 0. Or more general situation, when we integrate delta t minus a with this f t from this c to d, in that case the value of this integral is going to be f a when a belongs to this interval c to d, or it will be 0 when a is outside the range of c to d. So, this is a more general situation when we have this delta function under this integration with some function here f t t t, the value will be just f a whenever a lies between c and d. So, having these properties of the Dirac delta function, we can indeed now directly apply this Laplace transform of this delta t minus a. So, as per definition, we have e power minus s t and delta t minus a dt, and using this property here, since this a will this t goes from 0 to infinity, and whatever a we take here, a is certainly positive we consider. So, here in that case this a will lie in this interval of integration, and the value of this integration is going to be just the value of this function e power minus s t at t equal to a. So, that means e power minus a s, that is the value of this integral, and which is the Laplace transform of Dirac delta function. Just a short remark that there is no such function exists in the classical sense. So, one can think this delta t just as 0 when t is not equal to 0, and somehow infinity when t equal to 0. Okay, so, just another remark. So, we have already considered this Heaviside function, which is defined as whenever t is less than a, it is 0, and t greater than or equal to a, it is 1. And indeed, we have computed earlier the Laplace transform of this function u t minus a, and because in this case this will be just integrated from a to infinity, the function is 1, and then e power minus s t, and then we have d t. So, which can be integrated. So, we have e power minus s t over minus s, and then a to infinity. So, it will go to 0, then we have 1 over s and e power minus s a. So, that is the Laplace transform of this function, this Heaviside function u t minus a, or sometimes we denote here u a t, whatever way. So, and we also know that the Laplace transform of this delta function, Dirac delta function, is e power minus a s, and we will try to give some intuition that what is the relation between this Dirac delta function and this Heaviside function, because if we take a closer look at their Laplace transform, they are having e power minus a s common in both. So, we know already this derivative theorem that the Laplace of the derivative of this u a will be minus u a 0 and plus s l u a t. So, Laplace of this derivative of u a will be minus u a 0 plus s times this the Laplace of this. So, we can substitute this Laplace here, and what we will get, because this is going to be 0 and then we have s times the Laplace of this u a t, which is just e power minus a s. So, what we have observed that the Laplace transform of this the derivative is equal to e power minus a s, and in that case the Laplace, what we observe here, that the Laplace of the derivative of this Heaviside function, because the Laplace of the derivative of this Heaviside function is e power minus a s, and which is the Laplace transform of Dirac delta function. So, the Laplace transform of the Dirac delta function and the Laplace transform of the derivative of the Heaviside function, they are the same. So, that it seems like the derivative of this Heaviside function is the Dirac delta function from this conclusion, but that is also justified, because if we take a look at the definition. So, delta x minus a, if we integrate from 0 to t, what we will get? We will get the Heaviside function, because if this t is greater than a. So, this will contain in the interval, and the value will be 1 for t greater than a, the value of this integral, and 0 when t is less than a. So, we are getting here that the integral of this delta x minus a is equal to u t minus a. That means, in some sense this implies that the derivative of this Heaviside function is the Dirac delta function, and which is coming from this Laplace transform as well, because the Laplace transform of the derivative of the Heaviside function was equal to the Laplace transform of the Dirac delta function, and the same conclusion we are getting from this observation. So, in certain sense we can say, because this is again not the classical sense, because this Heaviside function is a discontinuous function, it has a value 0 when t is less than a, and then it has the value 1 when t is greater than a. So, this is a discontinuous function at this t is equal to a, and still we are talking about its derivative, and its derivative is Dirac delta function, which is again not a classical function, but what we observe that this Heaviside function, when we integrate the value, because it has a constant value here 0 and this is 1. So, its derivative is going to be 0 there and also 0 there. That means, whenever t is not equal to a, the derivative of this u hat is going to be 0 as per this implication, the Dirac delta function, and when t is equal to a, it is going to infinity, because this Dirac delta function takes a very high large value at t is equal to a. So, it is going to infinity, which is again indeed the case here, because the slope is infinity at this point. So, the derivative of this Heaviside function seems to be this Dirac delta function. Okay, just a problem here where we will find the Laplace inverse of s plus 1 divided by s. So, this s plus 1 divided by s can be written as 1 plus 1 over s, and then we can apply this Laplace inverse. So, we have Laplace inverse 1 and then the Laplace inverse 1 over s, and the Laplace inverse 1 is the Dirac delta function. So, delta t minus 0 or delta t, and this L inverse 1 over s, that is 1, the Laplace inverse of 1 over s is 1. So, we have 1 plus delta t, the value of this L inverse s plus 1 divided by s. Now, we will move to the next function, which is the Bessel's function, or rather Bessel functions, because it is a series of sequence of functions. So, the Bessel functions of order n. So, that order is important, and this is defined as, with this infinite sum j n t, the r goes from 0 to infinity minus 1 power r factorial n plus r, and then t by 2 n plus 2 r, and then n goes from 0, 1, 2, 3, etc. So, this is how this Bessel's function of order n are defined. So, of order Bessel functions of order n are defined, and this is of first kind. So, the Bessel functions, just to give you little more information, that this Bessel's function is a solution of the so called Bessel's equation of order n, and those ordinary differential equations are given as. So, here we have the nth order derivative of this y plus 1 over t y prime, and then we have here 1 minus n square over t square y equal to 0. So, the solution of this Bessel's equations come as this Bessel's function written as infinite sum. So, we will consider in this lecture now the Bessel's functions of order 0 and 1, and for the order 0, when we expand this will be coming as 1 minus t square over 2 square t 4, 2 square 4 square and t 6, then 2 square 4 square and 6 square and so on. And j 1, if we write, it will be t by 2 and t cube by 2 square 4, and then we have t 5 by 2 square 4 square and 6. And if we take a closer look at these two functions here, if we differentiate this. So, if we differentiate this function. So, 1 the derivative will be 0, then we have minus 2 t and then 2 square, then we have 4 t cube and then 2 square 4 square, then we have here 6 t 5 2 square 4 square and 6 square. And so, this 2 will get cancelled, this 4 will also get cancelled, and this 6 will also cancel this square. So, what we are getting then, minus this t by 2 plus here we have t cube 2 square 4, we have t 5 and 2 square 4 square 6 and so on. So, here if we take the minus sign out, we have t by 2, we have minus t cube by 2 square 4, we have t 5 2 square 4 square and 6. So, what we observe that the derivative of this j 0 t is nothing but minus of this j 1 t. So, we will note now that the derivative of j 0 t is nothing but j 1 t. Well, so we will now find the Laplace transform of j 0 t and j 1 t. So, the Laplace transform of j 0 t, that is the Laplace transform, we have 1 minus t square by 2 square, then we have t 4 2 square 4 square, we have minus t 6 2 square 4 square 6 square, that was the definition of the j 0 t. And now, we will apply this Laplace transform, this term by term, and so we will get the Laplace transform of 1, which is 1 over s, the Laplace transform of t square, which is factorial 2 over s cube, the Laplace transform of t 4, so factorial 4 over s 5, and the Laplace transform of t 6, which is factorial 6 over s power 6. And then we will just rewrite. So, if we take common this 1 over s, we will get 1 minus this 1 by 2 1 by s square, because this factorial 2 will get will cancel this square term. So, we have 1 by 2 1 over s square. Here in this case we will get, so here we have the 4 3 and 2. So, 1 2 will cancel this square, the 4 will cancel this square, and we have this 3. So, we have 1 by 2, we have 3 by 4, and then we have 1 by s power 4. Similarly, here we will get 1 by 2, 3 by 4, and this 5 by 6, and 1 over s power 6. So, taking note on this expansion, binomial expansion, what we have 1 plus x power minus n is 1 minus n x, and then we have n n plus 1 over factorial 2 x square, then we have n n plus 1 over n plus 2, and then we have here 1 product 2 product 3, and then we have here x cube. So, taking note on this, if we try to look at this and take this n is equal to half. So, we will precisely get this, because here we have this half it is matching there. So, when n is half, so n is half, we have 1 minus this 1 by 2, n is half, then half, and then 3 by 2. So, we will get precisely this one. Here also we have n, so half, we have 3 by 2, and we will get also here 5 by 2. So, that can be now written, this term can be written as that 1 over s, and this everything is 1 plus 1 over s square and power this minus half. So, more compact form. So, still we can simplify this, we have s square plus 1 over s square, and this s square will go up with the s. So, s gets cancelled, and we will get just 1 over 1 plus s square and the square root of it. So, having this, the Laplace transform of j 0 t is 1 over 1 plus s square square root t, and we know that the Laplace transform. So, we know that j 1 is equal to minus j 1 is equal to minus j naught derivative. So, we take the Laplace on both the sides here, the Laplace both the sides. So, we are getting this Laplace of j naught, this hat the derivative t, and then we have the Laplace of j 1 t is equal to, we use the derivative theorem here. So, it is a derivative, and minus s Laplace of j 0 t and plus j 0 0, and then so this Laplace of this j 0 will be 1 minus s, and the Laplace of j 0 t, that is going to be 1 over 1 plus s square. So, that we will put it, because j 0 is going to be 1 over this square root 1 plus s square. So, we can compute from there when t is 0, that means j 0 0, that is going to be 1 only, and then here s, the Laplace transform of j 0 t, that is coming from here. So, we can substitute now. So, we have 1 minus s over square root 1 plus s square, that is the Laplace transform of j 1. So, given the Laplace transform of j 0 t, we can apply this derivative theorem, and noting down that j 0 0 is 1. So, we can get that the Laplace transform of j 1 t is equal to 1 minus s over s square plus 1 square root. So, using the convolution theorem, we will prove now that this beta m n, which is defined as 0 to 1 u power m minus 1, 1 minus u power n minus 1 du, is given as factor gamma m gamma n divided by gamma m plus n. So, this result we have already proved in integral calculus, and now we will see it is much easier using this convolution theorem and the Laplace of the beta function. We can get this relation easily. So, if we assume this f t is equal to t power m minus 1 and g t we take t power n minus 1. So, we define these two functions and then consider their product, their convolution product. So, 0 to t, and then we have tau power m minus 1 t minus tau power n minus 1 d tau. So, this convolution is defined in this way, and then we substitute here tau is equal to u t. So, this tau u t and here also u t. So, if we define this tau is equal to u t and d tau will be t times du. So, our limits will be again, because when t is 0 we have 0 and then t is this tau is t. So, u will be 1. So, we have 0 to 1 the limits of this new integral, tau is replaced by u t. So, we have t power m minus 1 u power m minus 1. From there also, because we can take this t power n minus 1 common and then we will get 1 minus u power n minus 1 and d tau will be t times du. So, this t we can collect, we have m minus 1 and n minus 1 and then we have t there. So, m plus n minus 1 that is t, and we have 0 to 1 u power m minus 1 1 minus u power n minus 1 du, which is the beta function. So, this product, the convolution of these two functions f and g is coming as t power m plus n minus 1 and the beta function. So, having this result that the convolution of these two functions gives us the beta function with this t power m plus n minus 1, we can make use of the Laplace transform and in particular the convolution property of Laplace transform, which we have discussed before. That means, the Laplace transform of this t power m plus n minus 1 b m is equal to the Laplace of this convolution, and that is a convolution property, that the Laplace of the convolution there will be equal to the product of the Laplace of f and g. So, having this product, so L we have t power m minus 1, the Laplace of t power n minus 1, and we have the product there. So, this Laplace of t power m minus 1 we know already. So, it is gamma m over s power m, and for t power n minus 1 also we know gamma n over s power n. That means, we have here gamma m gamma n over s power m plus n, and here we have the Laplace. So, now if we take the inverse Laplace transform, what will happen? We will have here t power m plus n minus 1 and this beta m n, the Bessel function m n, and then here we have the right hand side, this is gamma m gamma n and the Laplace inverse of 1 over s m plus n, which is t power m plus n minus 1 over the gamma m plus n. So, this gives us now that this beta m n is equal to gamma m n divided by gamma m plus n plus 1. So, considering these two functions t power m minus 1 and t power n minus 1, we have established this relation that this convolution product is equal to this beta function with the multiplication of this t power m plus n minus 1, then we take the Laplace transform and then the inverse Laplace transform, and we readily get this beta m n in terms of the gamma m n. The last one, we have the Laguerre polynomials, which are defined as ln t e power t over factorial n and the derivative n, the nth order derivative of e power minus t t power n is 0, 1, 2 and so on. The Laguerre polynomials are the solutions of these Laguerre differential equations given in this form: x d 2 y dx square 1 minus x dy and n y is equal to 0. So, this is the Laguerre differential equation, and the solution will be given by this in the form of Laguerre polynomial. So, here it is written in terms of x. So, naturally, this ln can be also written in terms of x. Here we will show that the Laplace transform of these ln t is nothing but s minus 1 power n over s power n plus 1. So, if we consider with the definition, so we have e power minus s t, here these are the Laguerre polynomial, and we have to integrate this with respect to t. So, 1 over factorial n that we can take out, and then exponential we have e power minus s t and e power t, this one. So, we have merged these two, and then the nth order derivative of e power minus t t power n. And now we can integrate this by parts. That means, e power minus s minus 1 t as it is, and we will integrate this one. So, one order will be reduced here, then the limit 0 to infinity. Now, we will differentiate this there. So, s minus 1 factor will come with negative sign, which will make this sign positive here. 0 to infinity e power minus s minus 1 t, then we have n minus 1th with e power minus t t power n, and then dt. This first term, if we see here, when t goes to infinity, because of this exponential term, this will vanish, and when t goes to 0, because we have this n minus 1th derivative of this e power minus t t power n. So, in each term, when we differentiate this, the t will survive, and when t goes to 0, this will be 0. So, this because of infinite the infinity, because of this exponential term, this term will vanish, and because of this t power n, and we are talking about n minus 1th order derivative. So, in each term t will appear, and when t goes to 0, this will go to 0. So, the whole term this will go to 0. So, we will remain with s minus 1 over factorial n, and then the integral here, which 0 to infinity e power minus s minus 1 t, we have n minus 1th order derivative of this e power minus t t power n dt. So, the Laplace of this will be s minus 1 power n, and because we have to now continue this process of integrating. So, every time we will have a reduction here till we got this derivative power 0, that means no derivative. So, here parallelly this power will increase. So, we will have this n times differentiation or this process. So, we will get here power n, and then we have these term without the derivative there, which can be written now the s power s minus 1 power n over factorial n, and here this is e power minus s t, because this is minus t there and plus t will cancel out. So, e power minus s t and t power n, which is the Laplace transform of t power n, and which we know the result, that is factorial n over s power n plus 1, and then we can combine or we can cancel these two. So, we got this s minus 1 power n over s power n plus 1. So, these are the references we have used for preparing this lecture. And just to conclude, so in this lecture we have considered the Dirac delta function, which was defined as that the delta t minus a is equal to 0 whenever t is not equal to a, and this integral t delta t minus a f t dt is always equal to f a and 0 if this a lies between c and d, otherwise it is 0. The Bessel's function we have discussed, and we have computed its Laplace transform for the case when j is 0 and 1. We have also discussed this Lagrange polynomial and ln(t). So, here also we have computed its Laplace transform for this general case, and that is all for this lecture, and I thank you for your attention.